In this chapter, we're going to be going over the counting principle once again and permutations. So recall the counting principle that we've learned previously. The counting principle says if the first experiment can be performed m distinct ways and a second experiment can be performed n distinct ways, then the two experiments in that order can be performed m times n ways. So we multiply. So let's do a couple examples here. So the first example, a password used to gain access to a computer account is to consist of 2 lowercase letters followed by 4 digits. To determine how many different passwords are possible, if the first one says the repetition of letters and digits is permitted. So we have 2 letters followed by 4 digits. So I just put LL for letter and then DDDD for digit. So we have repetition is permitted. So that means we have 26 options for the first one, 26 letters, times we have 26 letters for the second one because repetition is allowed. Digits, we have 10 digits. And since we can allow repetition, we have 10 digits for all of these. So we're going to multiply this together. And we end up getting 6,760,000 different possible arrangements. Okay, and let's do it when repetition is not permitted. So once again, we have letter, digit, 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 digit. So we have 26 options for the first one. Since repetition is not permitted, that means we only have 25 options for the next one. And then for digits, we have 10 options for the first one. Repetition's not allowed, so 9 options for the second one, 8 options for the third one, and 7 options for the last one. Okay, so multiply all of these together, and we end up getting 3,276,000 different possible arrangements. And for the last one, the first letter has to be a vowel, A, E, I, O, or U, and the first digit cannot be 0, and repetition is not permitted. Okay, so let's kind of write down what we've had written down before. 2 letters, 4 digits. So if the first letter must be a vowel, that means we only have 5 options to choose from. The second one can be any letter, but since we took one of them out for the vowels, there's only 25 options left. Repetition's not permitted. For digits, the first digit cannot be a 0, so there's only 9 options. And the rest of the digits can be anything. So since it can be anything, but we took out one of them, it's going to start at 9, and then the other ones are going to be 8 and 7. Because repetition is not allowed. Okay, so we multiply these together. 5 times 25 times 9 times 9 times 8 times 7. We get 567,000 different arrangements. Okay, let's do a couple other examples here. And then we'll see how this relates to permutations. So at Old Navy, a supply of solid colored t-shirts has just been received. The t-shirts come in green, blue, white, yellow, or red. And Billy, the floor manager, decides to display one of each color t-shirt in a row on a shelf. Question A says how many different ways can he display the 5 different color t-shirts on the shelf? So we have 5 options for the first one. We have 4 options for the second one because we can't have any repetition because we need to display all of the colors. 3 options for the third one, 2 for the fourth one, and then at that point there's only going to be 1 left over, so 1 option for the last one. So this is just the counting principle. Once again, we multiply all these together. We get 120 different ways he can display the 5 different color t-shirts. Okay, and then for the next one, we have if he wants to place the blue t-shirt in the middle, how many different ways can he arrange the shirts? Okay, so we have 5 slots. The blue has to be in the middle. That means there is only 4 options for the first one because blue is not an option, so there's only 4. No repetition, so we have 3 options left. The next one is the middle shirt. The middle shirt has to be blue, so that means that has only 1 option. And then for the fourth one, we kind of pick back up where we just left off a second ago. Now there's only 2 more colors left. And then for the last one, there's only 1 color left. Okay, so it's kind of like we were doing the same thing we've been doing, but we skip the middle one because it had to be blue. And now we multiply these together. 4 times 3 times 1 times 2 times 1 is going to give us 24 different ways, with blue having to be in the middle. And the last one, if Billy wants the white t-shirt to be first and the blue t-shirt to be last, and how many different ways can he arrange the t-shirts? So there's only 1 option for the first one because it has to be white. And for this one, what I'm going to do is I'm going to put some blanks here. Blank times blank times blank times. The last one has to be blue. So the last one has to be blue. So there's only 1 option for that one, has to be blue. So now we're left with 3 t-shirts. So what it's going to be for the middle ones is we have 3 options for the second one, then 2 options left for the third one, and 1 option left for the fourth one. So we multiply all of these together and we get 6 only. So there's only 6 different ways that we can arrange them if we are saying the first one and the last one have to be one of these specific shirts. So you can see just by narrowing it down like that, it went from like 120 to 6. Okay, so this brings us to permutations. So a permutation is an ordered arrangement of objects. So ordered arrangement of objects is a permutation. The number of permutations, so the number of ordered arrangements of n number of distinct objects is n factorial. So we put a little exclamation point and we read that as n factorial. This tells us how many different ways we can put objects in order. So n factorial, what this actually means is it's going to be the number itself times 1 minus the number, or times the number minus 1, times the number minus 2, and you keep on subtracting 1 until you get to 3, 2, 1. Okay, so when determining the number of permutations, we assume that repetition of an item is not permitted. So for example, if we have the names Adam, Michael, Jim, and then we also have the names Michael, Jim, Adam, these are 2 different permutations of the same 3 names. So order matters since these are not in the same order. These are not the same, they don't represent the same permutation. So let's just evaluate some of these to get some practice doing it by hand. There's also a button in the calculator under the PRB button for probability. And for the first one, we have 5 factorial. So 5 factorial is going to be 5 times 4 times 3 times 2 times 1. So it's just as easy as that. Just multiply the number and then 1 less than the number all the way to 1. And this is going to give us 120. And next, let's do 3 factorial. That's going to be 3 times 2 times 1. That's going to give us 6. So you probably can tell that you don't have to write times 1 because that's not going to change anything. 1 factorial is just 1. The next one is a little bit tricky. We have 0 factorial. 0 factorial is actually equal to 1. So if we think about what it actually means for this factorial, 3 factorial tells us how many different ways we can arrange 3 objects in order. So 0 factorial tells us how many different ways we can arrange 0 objects in order, which doesn't seem like it makes sense, but the number of ways we can do that will be just one way, and that's just essentially not arranging anything in order. So it's a little bit odd thinking of it that way, but just remember 0 factorial equals 1 and not equal to 0. Okay, so for this example, how many different ways can we arrange 5 books on a shelf? So we are taking 5 books and seeing how many different ways we can put them in order. That's going to be permutation 5 factorial, 5 times 4 times 3 times 2 times 1. That's going to give us 120 different ways. And for the next one, let's say there are 3 Olympic teams, USA, Sweden, and Canada. We want to know how many different standings are possible for first, second, and third place. So clearly order matters here because we're ranking them first, second, and third. So since there are 3 teams and we're ranking them first, second, and third, that's going to be 3 factorial, which is 3 times 2 times 1, which gives us 6 different standings, 6 possible different standings for arranging those 3 Olympic teams. So let's go ahead and actually list them all out. So the first way, we could have USA, Canada, Sweden in that order. The second way, we can have USA, Sweden, Canada. And then we can have Canada, Sweden, USA, or Canada, USA, Sweden. And then for the 5th option, we have Sweden, Canada, USA. And then the last option here is going to be Sweden, USA, and then Canada. Okay, so those are all of the possible permutations for these 3 Olympic teams coming in first, second, and third, assuming those are the only ones we're looking at. Okay, so let's do something a little bit different. We're going to make it a little bit more complicated. So instead of choosing all of the objects and putting them in order, we're going to choose a certain amount of the total objects and put that certain amount in order. So we're going to have n total objects. We're going to take r of them and put them in order. So we say that this is permutations of n objects taken r at a time. And the formula that we get for this is going to be written like this. NPR equals n factorial divided by n minus r factorial. So you have to subtract the n minus r first in the denominator and then take the factorial of that. Okay, so just kind of recognize here, if we take all n objects and put them in order, the formula becomes npn, because the r becomes an n because we're taking all n of the objects. So plugging in an n where the r was, we get n factorial divided by n minus n factorial. The denominator becomes 0 factorial because n minus n is 0. We know that equals 1. So n factorial divided by 1 is just n factorial. So that's the formula that we just used on the previous page. Okay, so let's get some practice doing these ones. So this button is also on the calculator. It is under the PRB button. So evaluate the following. We have 4p2. So based on the formula, this is going to be 4 factorial over 4 minus 2 factorial. That's 4 factorial over 2 factorial. And let's go over a shortcut way to do this. We can always cancel that denominator with a portion in the numerator. So the numerator is actually 4 times 3 times 2 times 1, right? 4 factorial. The denominator is 2 times 1. We can cancel off 2 times 1 divided by 2 times 1 because they're exactly the same. We're left with 4 times 3, which gives us 12. So this shortcut's always going to be available, so I recommend using it if you're doing this by hand. So this means that if we had 4 objects and we're going to take 2 of them and put them in order, there is 12 different ways that we could do this. Next one, we have 5p1. So 5p1 is going to be 5 factorial divided by 5 minus 1 factorial, which is 5 factorial divided by 4 factorial. So if we were to write this out, it would be 5 times 4 times 3 times 2 times 1 divided by 4 factorial, which is 4 times 3 times 2 times 1. 4 times 3 times 2 times 1 can cancel, and we're actually just left with 5. Okay, and then the last one here, we have 7p3. 7 factorial over 7 minus 3 factorial. That's going to give us 7 factorial over 4 factorial. So hopefully you recognize now that that 4 factorial is going to be canceled. So what I'm going to do in the numerator, I'm going to write this as 7 times 6 times 5 times 4 times 3 times 2 times 1. That's the same as 4 factorial. 4 factorial is 4 times 3 times 2 times 1. So if we leave it like that, then we can put the denominator, leave it like that. 4 factorial divided by itself cancels. We're left with 7 times 6 times 5. And that's going to give us 210. So there's 210 ways to pick 3 objects from 7 objects and put them in order. So let's do this example here. You are among 9 people forming an astronomy club. Collectively, you decide to put each person's name into a hat and randomly select a president, vice president, and secretary. So we want to know how many different arrangements or permutations of officers are possible. So we know that order matters here because these positions are different. We have president, vice president, secretary, so order matters. So this is going to be 9 total people, and there are 3 total positions. So this is going to be 9p3. We're taking 3 out of the 9 and putting them in order and seeing how many ways we can put them in order. So this is going to be the formula 9 factorial divided by 9 minus 3 factorial. So in the denominator, that gives us 6 factorial. So we could go ahead and know that 6 factorial is going to be canceled. It's going to be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. I'll go ahead and actually write this one out, unlike the last one, in case it didn't make too much sense. So that's going to be divided by 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1. And they cancel with the ones from the numerator. They completely cancel. We're left with 9 times 8 times 7. This is going to give us 504. So there's 504 different arrangements. Okay, so let's do one more of these ones. So let's say, before you do the next one, let's say you didn't simplify it and you multiplied the whole entire numerator, 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and you multiplied that whole denominator, 6 times 5 times 4 times 3 times 2 times 1, you're going to get a big number divided by a big number. You just have to divide those and get 504. Okay, last example for this one, and then we'll get into the last thing. 43 cars are at a Daytona race. We want to know how many ways can they place first, second, third. So there are 43 total cars, and we're going to arrange them in order, and it's going to be first, second, and third. So this is going to be 43 P3, and this is going to be 43 factorial divided by 43 minus 3 factorial, which ends up being 43 factorial divided by 40 factorial. So this one's a little bit messier. So for the numerator, instead of writing out 43 times 42 times 41 all the way to 3 times 2 times 1, I'm going to write this out the way I did it before. 43 times 42 times 41 times the rest of it is 40 factorial. And the reason why I stopped there is because the denominator is 40 factorial, and you know that those are all going to cancel out if you wrote them all out. So it just kind of saves you some time for having to write them out. So multiplying 43 times 42 times 41, that's going to give us 74,046 different ways. So usually these numbers are going to be a little bit bigger than you might think of initially in your head. Okay, for the last thing here, it's the last formula we're going to be using. It's permutation of duplicate items. So we may want to order a group of objects where some of those objects are the same. So let's say, for example, we have this set of objects, A, B, B, C. Originally, we would say that we can order these objects 7 factorial different ways because we have 7 of them, so 7 factorial, but there's repetition among those objects, so not all permutations are going to be distinguishable. We can end up switching some of the A's, but it'll look exactly the same. So since some of these objects repeat themselves, this next formula we're going to use is going to essentially divide off the permutations that are not distinguishable. So this next formula is going to be our duplicate items or distinguishable permutations formula. The number of distinguishable permutations of n objects, where n1 is going to be the number of the first type of duplicated items, n2 is the number of the second type of duplicated items, and so on, is going to be n factorial divided by n sub 1 factorial times n sub 2 factorial, and you keep on going until n sub k factorial, which the k is going to be however many sets of duplicate items there are. So let's see this in an example so it makes some sense here. So let's find the number of distinguishable permutations for A, B, B, C. So first, let's go ahead and count how many total objects we have. We have 1, 2, 3, 4, 5, 6, 7. So n is going to be 7. And let's count how many groups of objects we have that are the same. So we have A's. So let's let n sub 1 be the number of A's. There are 4 A's, so n sub 1 is 4. Let's let n sub 2 be the number of B's. There are 2 B's, so n sub 2 is 2. N sub 3 is the number of C's. There's only 1 C here, so that's actually not even going to play any role into this, but we can include it if we want. So that means the formula is going to be n factorial, or n factorial, I was reading distinguishable at the same time, n factorial divided by n sub 1 factorial times n sub 2 factorial times n sub 3 factorial. So we knew to stop at 3 because that's how many replication groups that we had. So let's plug in our values. So it's going to be 7 factorial divided by 4 factorial times 2 factorial times 1 factorial. So let's go ahead and just leave out the 1 factorial. 7 factorial over 4 factorial times 2 factorial, because 1 factorial is just 1. So we have some options here. We can multiply out the numerator and denominator. 7 factorial, boom, get a number, put it in the numerator. And then in the denominator, 4 factorial times 2 factorial, multiply that whole thing out, put it in the denominator, and then divide it. That's completely fine. I like to use the shortcut method. I'll write out this one completely. 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 times 1, divided by 4 factorial is 4 times 3 times 2 times 1. 2 factorial is 2 times 1. So since we just wrote it out, I always cancel the larger factorial in the denominator. So it's 4 over 4, 3 over 3, 2 over 2, 1 over 1. Those completely cancel. We can cancel the 2 that's left over using the 6. 6 divided by 2 is 3. Or we can just multiply the numerator and divide by 2 times 1, which is 2. So whichever way you do it, we're going to end up with 105 distinguishable permutations. So the way that I mentioned it with the 6 divided by 2, you would take a look at this 6 and this 2. I picked the 6 because 2 goes into 6. And you could say that 6 divided by 2 is going to give us a 3. And then 2 divided by 2 is 1, so it cancels. The 1 in the denominator doesn't play any role here. Dividing by 1 doesn't change anything. So the answer would just be 7 times 3 times 5, which is just 105. Okay, and then for the last one, how many distinguishable ways can the word Cincinnati be arranged? So first, let's determine how many objects we have total. So that's going to be n. N is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's the number of letters in the word. And let's let n sub 1 equal the number of C's in Cincinnati. So there are 2 C's in Cincinnati. Let's let n sub 2 be the number of I's. And there's going to be 3 I's in Cincinnati. And let's let n sub 3 be the number of n's. And there are 3 n's in Cincinnati. And that's really all we have to do. We can do T and we can do A, but since there's one of each, it's not going to change anything. So if we included them, we would have had n sub 4 equals 1, n sub 5 equals 1, just like we did in the previous one, but we don't have to. So let's go ahead and set this up. It's going to be n factorial divided by n sub 1 factorial times n sub 2 factorial times n sub 3 factorial. So this one has 3 different n's in the denominator also. It doesn't always have to be 3. So that's going to be 10 factorial divided by 2 factorial times 3 factorial times 3 factorial. And if we go ahead and write all of this out, that's going to be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And in the denominator, 2 factorial 2 times 1, 3 factorial 3 times 2 times 1, 3 factorial 3 times 2 times 1. So let's go ahead and cancel things out here. So let's cancel out 3, 2, 1 with 3, 2, 1. Okay, so once again, when we get to this point, you can just multiply the whole numerator together, multiply the whole denominator together, and then just divide those results, and you'll get your answer. I'm going to do it the cancellation way just to show us that we can cancel it. So what we can do is we can actually recognize that 2 times 2 in the denominator equals 4. We have a 4 in the numerator, so we can cancel off 2 times 2 in the denominator with the 4 in the numerator. And then we can cancel off the 3 in the denominator with the 6 in the numerator, because 6 divided by 3 is 2. So 6 divided by 3 is going to give us 2. And then in the denominator, the 3 cancels. 3 divided by 3 is 1. So now we're just left with 1 times 1 in the denominator, which is just 1, so we can ignore it. So we're left with 10 times 9 times 8 times 7 times 2 times 5. And this will end up giving us 50,400 different arrangements. Okay, so that means we can arrange the letters in Cincinnati 50,400 distinguishable ways. So that divides off the repetition between the letters that would have been the same. Okay, so that is it for this section with permutations.